Okay, welcome to Robotics 1. Since this is an undergraduate class, I'm gonna start with some very basic concepts. And I trust all of you know this, but I want you to understand that the easiest way to learn is something called as the chain link method, which means whatever you know, if you keep on adding links to it, that would help you strengthen your understanding. So I'm going to start from the very basic, and then we will gradually build upon the robotics. So step number 1, can someone tell me what is a vector?
It's a magnitude given direction.
Its magnitude and direction. So which means if you are in ISTB 12 and if you need to go to the student union, I can't just tell you that walk 5 units. You will never know like which direction to walk. I need to tell you go in the northeast direction, south direction, east direction. So vector, I'm going to call this vector OA. Vector is defined by the magnitude and vector is given by the direction. So you have OA. Now, whenever you see the vector, it has a start point and the end point. Vector starting from O going towards A. Everyone understood this? Next thing is scalar. Scalar only has magnitude, no direction. Example of vector is velocity. Example of scalar is speed. Now let me ask you a funny question. Which quantity, there is only one quantity that can be considered as a vector and a scalar, depending upon the context? Okay. What is rate of change of velocity? Acceleration. What is rate of change of speed? It's also acceleration. So if you refer some old textbooks, you will notice that at one time, acceleration was considered to be a scalar and a vector, because you can take the rate of change of velocity as acceleration. Sometimes you can take rate of change of speed as acceleration. But nowadays, current convention is acceleration is treated as the vector. Now, let me see. So let's understand. So you have this vector. I'm going to show you this vector. So this is, you are at origin and you want to go to this point A. You are at origin, you want to go to this point A. This is your x-axis. This is your y-axis. Your x-axis, this is your y-axis. And I'm saying that to get to A, you need to travel 3 units in x direction and maybe 4 units. And I need to draw, so 4 units in y direction. So to go from O to A, I need to travel 3 units in x direction and 4 units in y direction. So 1, 2, 3, 1, and 4. 4 units in y direction. So another way of writing this is identifying a unit vector. So unit vector, as the word says, it's a unit vector unit vector has magnitude 1. Unit vector only has direction. So if you travel 1 unit in I direction, it says, you can say that travel 1I. 2 units in I direction, 2I. 3 units in I direction, 3I. Similarly, you can have a unit vector in Y direction, which is J. So if you travel 1 unit in J direction, 1J, 2 units in J direction, 2J, 3J, and 4J. Everyone understood this? So I can state something like this. To go from O to A, you need to travel 3I plus 4J. Or I can say you can go 4J and 3I. Doesn't matter. As long as you travel 3 units in I direction and 4 units in J direction, you are going to get to this point. Now, please notice that this is a right angle triangle. This is a right angle triangle. So the magnitude of this vector, so this is, I'm going to call this OA. Magnitude of this vector OA is given as 3 square plus 4 square square root. So this is going to be 5. Because this is a right angle triangle, it's a Pythagorean theorem. You agree with me? I can also resolve this OA onto x-axis and I can resolve OA onto y-axis. Now I want you to understand this very important thing. So I'm going to say this angle is theta. This point is OB and this is A. So I have this triangle is triangle ABO, where the hypotenuse of this triangle is 5 units. I can say OA is equal to 5 units. This is the magnitude of OA. I can say OB is equal to OA cosine of theta. I'm going to call this theta x. I'm going to call this cosine theta x. So 5 cosine, so I can take the cosine component. I can also say AB is equal to OA sine theta x. So what I have done is I have resolved this vector OA into its component. And why resolution is important? Because I want you to note, remember there are 2 vectors. One vector arrow is pointed towards right. The other vector arrow is pointed up. So this vector is representing 3I and the other vector is representing 4J. So you have this vectorial representation and the final resultant vector, and which is very important. So OA vector is nothing but OB plus BA. OB plus BA. And you can see this O comes from here, A comes from here. So when you combine these two, BB gets cancelled and you are left with OA. Now, what I want to do is, I want to write what is cosine theta x, cos theta x. Cosine theta x by definition is 3 divided by 5. You agree with me? Now, what I'm going to do is, I'm going to actually give you one more angle. and that angle, I'm gonna say maybe theta y. I'm gonna say theta y. Do you agree with me that theta y is 90? So basically, since there's a right angle triangle, theta x plus theta y is equal to 90 degrees. In other words, sine theta x is equal to cosine theta y. Do you agree with me? I can also write this down as cosine theta x is equal, so cosine theta y is equal to 4 by 5. Do you agree with me? Now, I want you to notice that if I want to go from point O to B, O to A, the conventional method is go from O to B, turn 90 degrees, and go from B to A. Travel from O to B, turn and go up to A. However, some of you may say, why don't I orient myself in the direction of OA and just walk 5 units? So rather than going in this direction and in this direction, I stand here, I just angle myself in this direction and travel 5 units. That's perfectly fine. But the question is, how do you know how much to turn? But you already know the value of cosine theta x. You already know theta x, theta y. So you can find out the values of theta and orient yourself. Now, but I'm going to give you a slightly different approach. I'm going to say that the unit vector in OA direction is n hat. So what has happened? To travel in x direction, you have the unit vector I. You are traveling 3 units in I direction. To travel in y direction, the unit vector is j. You are traveling 4 units in j direction. And finally, you get to the final destination. Instead, I'm going to tell you that orient yourself in the n hat direction. Orient yourself into n hat direction and walk 5 units. Now the question is, how do we find out n hat? So what is I? I is a unit vector. What is j? J is the unit vector. So how do you find out the unit vector? To find unit vector, you have the vector. So for an example, if I do OA, this is the vector, and I divide that by the magnitude of OA. Because if I have a vector and if I divide that by the magnitude of OA, I get the unit vector. Do you agree with me? So what I want to do is, I want to find out what is n hat. N hat is unit vector in direction. Unit vector does not give you magnitude, it only gives you direction. Direction OA. So n hat, I can write this down as vector OA divided by magnitude of OA. OA divided by magnitude of OA. So I'm going to write OA. As you know, OA is 3I divided by 4j. Magnitude of OA, we already know, 5. And I want you to note, this attends the form 3 by 5I plus 4 by 5j. And Do you agree with me that 3 by 5 is nothing but cosine theta x? 3 by 5 is nothing but cosine theta x multiplied by I hat, and 4 by 5 is nothing but cosine theta y g. Do you agree with me? Now I want you to understand this equation has profound significance. What does this equation represent? This represents a unit vector in an arbitrary direction. A unit vector in the arbitrary direction is the direction cosine in I plus direction cosine in j, or you can have direction cosine in k. What does that mean? It means cosine theta x. What is theta x? Theta x is the angle made by that vector with respect to positive x-axis. This theta x is the angle between the vector and y-axis. This angle, so again, theta y is the angle made by that vector with positive j-axis. So if you have a robot and that robot has an arbitrary arm, and if you want to write down the equation for that arm, then what you can do is you can use this formulation. You can find out what is the direction cosine with respect to I, and then the unit vector is going to be cosine theta xi, cosine theta yj. So now you may ask me, how does this relate to robots? Now imagine instead of this vector, what I'm going to do is I'm going to give you a problem wherein what you have is you have a cylinder assembly. You have the cylinder assembly, and then you have this cylinder is able to pivot around x-axis. Now this is actually a robot. So what you have is you have a prismatic joint, which is like extension or a lead screw connected to a hinge or the revolute joint. So you have a prismatic joint connected to the revolute joint. And there are different ways. There are many ways you can come up with the equation for the location of the end effector. Now, for example, in this particular configuration, this is the end point. So this is called as the end effector. So if I ask you to, and if this distance, I'm going to give you this distance is d. If I'm going to give you this distance as d, you can easily tell me that this is d cosine theta, and this distance is d sine theta, and there are two variables. This angle can change and this extension can change. So this is a 2 degree of freedom robot. And the forward kinematics problem for this robot, is given theta and d. These are nothing but the joint parameters or joint values. Find position of end effector. Or EE. So this is the planar robot. So I'm going to say the end effector position is PX and PY. And you can tell me PX is equal to d cosine theta, py is equal to d sine theta. I can also ask you, hey, I don't want this position to be written something like this. Since this is px, this is py, I can write, and this I need to tell you, this is called as the forward kinematics problem. Forward kinematics. This is called as the forward kinematics problem. So I can say it is px I plus py j. So this is nothing but O, and I'm going to call this E. So OE is given by pxi plus pyj. So given the values of d and given the values of theta, you can find out the position vector or the end effector position in x, y, and z. This is a simple planar robot, so everything is great. Now, can someone tell me, I have represented OE in terms of I and j. Can I represent OE in terms of a unit vector that is oriented in the direction of the robot? But what is the difference between the unit vector I, unit vector j, and this unit vector n? So for an example, this is your j, this is your I. You agree with me, I and j's are fixed. They are not rotating. I and j's are fixed. So this is called as the fixed or inertial coordinate frame. This is called as the fixed or the inertial coordinate frame. So fixed or inertial coordinate frame. But nobody has prevented me from writing the expression OE is equal to. So once I know the value of d n hat. Are you with me? But what is the difference between that n hat vector? What is the difference between that n hat vector and the vector I and j? That n hat vector is attached to the robot and is moving with the robot. You agree with me? On the other hand, i's and j's, they will remain fixed. So if I want to find out the position OE, now some of you may ask me, can we just replace n in terms of i's and j's? Absolutely. You can replace. So if I want to convert, it's extremely important. If I want to convert equation 1 into equation 2, that is extremely important. What I do is I replace n hat, which is the unit vector that is attached to the robot, in terms of the unit vectors which are fixed. And do you agree with me? I already gave you the answer to this. D. What is n hat? N hat is nothing but cosine theta x I plus sine, actually cosine theta x, let me be more, cosine theta y j. Cosine theta x, here theta x is nothing but theta, so cosine theta x is d cosine theta x I plus D, cosine theta y. Cosine theta y is nothing but sine theta x. Sine theta x g. And can you see that you have the same expression that you started with? Everyone understood this? Now, what did we do? We did a very important step, which is called as the coordinate transformation. What is coordinate transformation? Whenever you have a robot would have different coordinate systems. So the first coordinate system will be inertial or fixed, but all other coordinate systems will be attached to the links. These links are going to move, and which means the coordinate frames are also going to move. So I want to understand the relationship between the first frame and the frame that is moved, or the second frame. So you need to understand how the coordinate transformation takes place. So clearly, there is one unit vector. So what I want to do is, I want to derive the most general expression for the coordinate frame, wherein you have this initial coordinate frame. I'm going to call this x naught, y naught, and you have this rotated coordinate frame, which I'm going to call x1 and y1. So, and I want to find out the relationships between these two coordinate frames. These two coordinate frames are perpendicular to each other. So do you agree with me that this angle of rotation is going to be theta? So now what we did here, and I want you to understand what we did here. We had this initial coordinate frame and we had this n hat vector. And then I resolved that. But now what I want to do is, I want to look at the most general case wherein you have two coordinate systems which are perpendicular to each other and then they are rotated. So I want to find out projection of new coordinate frame x1, y1 on old coordinate frame x0, y0. Again, I'm gonna give you a break for 15 minutes and then we will phenomenal. Okay, so now here is the problem. We have two coordinate frames. Now let me define. So what you have is a coordinate frame has three vectors. So when you say three vectors, you have I, J, and K. So you have X, Y, and Z. You have X, Y, and Z. In robotics, we always use right-hand coordinate system. What do I mean by right-hand coordinate system? So basically, we use right hand, and then we have three fingers. Thumb is pointing towards the X direction, with first finger in Y direction, and the middle finger in the Z direction. Why is this coordinate system important? Because in robotics, you are going to have three-dimensional systems. So things will be floating around and rotating. So you have to make sure you always use right-hand coordinate system. In this particular case, you have x0 and y0, but this goes without saying z0 is coming out. Everyone understood this? Here, you have x1 and y1, but it goes without saying that z1 is coming out. And z0 and z1, they are aligned. Do you agree with me? So you have x, y, z, x1, y1, z1. Now, whenever you have a right-hand coordinate system, we have to identify the positives and negatives. If you travel in the positive x direction, that is positive. If you travel in positive y direction, it's positive. If you travel in positive z direction, it's positive. And vice versa. If you go in opposite direction, it's negative. However, if you want to find out the sign for the angular motion, then remember, curl your fingers in the direction of rotation. So you have this rotation, curl your fingers in the direction of rotation, and your thumb is pointing towards positive x-axis. So this rotation is positive. If your rotation is in the opposite direction, curl your fingers. If the rotation was like this, your thumb will be in the direction of negative x. So that rotation would be negative. About y, curl your fingers in the positive y direction, and this rotation is going to be positive. And if you have, so this rotation will be positive. So please note, this theta rotation that we are doing is a positive rotation, which means the new frame is rotated in the positive theta direction. It's in the positive theta direction. So the relationship is positive. So always remember right hand coordinate system, curl your fingers in the direction of rotation. If your thumb is pointing towards positive axis, that rotation is positive. Now, one thing I want you to understand is we will always go from the old frame to the new frame. So the first frame that we have is x naught. We are going from x naught to x1. If you have x2, then you are going to go from x1 to x2. If you have x3, then x2 to x3. And as your robots has more and more links, each of these frames will be associated with that link. The first frame, which is x0, y0, is inertial frame. It's not moving, but all the frames, all the subsequent frames will be moving. So idea here is, I want to find out the relationship between the next frame to the previous frame. Now I can write this something like, I want to find out projection of new frame on old frame. So in this case, I want to find out projection of x1, y1 on x0, y0. Do you agree with me? Do you agree with me? Projection of, projection on. How do you find out projections? By drawing perpendiculars. Do you agree with me? So first, I want to find out projection of x1 and y1 on x0. Projection of x1, y1 on x0. What should I do? I will draw perpendiculars. This activity is extremely important because I'm going to ask you a quiz problem based on this activity. So make sure you understand what I'm doing. So I want to find out projection of x1 and y1 onto x0. So I have drawn perpendicular onto x0. This is positive x0. This is negative x0. Positive x0, negative x0. So do you agree with me? Since the angle is theta, this guy is x1 cosine theta. And since this angle is theta, this guy is y1 sine theta. Do you agree with me? The only difference is x1 cosine theta is aligned with positive x0. y1 sine theta is aligned with negative x0. You agree with me? Because this projection is going in this direction and this projection is going in this direction. So if I want to write this down, I can say x0 is equal to plus x1 cosine theta minus y1 sine theta. Do you agree with me? Everyone understood that why y1 sine theta is negative? Because it is aligned with the negative x0 axis. This x1 cosine theta is aligned with positive x0 axis. Now I want to find out projection of x1 y1 onto y0. x1 y1 onto y0. What should I do? Perpendiculars. So this is one perpendicular and this is the second perpendicular. And you guys can tell me that this distance is going to be x1 sine theta and this distance is going to be y1 cosine theta. Do you agree with me? In both the cases, I want you to observe that both the projections are aligned to positive y0. Once again, projection of y1 onto y0 is positive. It would be y1 cosine theta. Projection of x1 onto y0 will be x1 sine theta. It's going to be positive. So which means y0 is going to be x1 sine theta plus y1 cosine theta. Do you agree with me? And now if I ask you, what is the projection of z1 onto z0? Projection of z1 onto z0. You will tell me z0 is equal to z1. Why z0 is equal to z1? Because if you look at the first triad, x0, y0, z0. Second triad, x1, y1, z1. z0 and z1, they are aligned. Because this is the rotation about z. Do you agree with me? Okay. What I want to do is, I have this algebraic equation. I want to write this as a matrix vector equation. How do I do that? This can be done something like this. I would say x0, y0, z0. Then you have this 3 by 3 matrix. And then you have x1, y1, z1. And this matrix is a 3 by 3 matrix. So first row, second column, third column, second row, first column, second column, third column, third row, first column, second column, third column. We have to fill in the blanks. Can someone tell me what would be here? Cosine theta. And if you haven't studied linear algebra, don't worry about it. I will explain it to you what this means. So you have cosine theta. Then you have minus sine theta multiplied by 0. So now this, what I have done here, is represents the very first equation that you have. How do you perform matrix multiplication? First row, first column. Cosine theta multiplied by x1 plus minus sine theta multiplied by y1 plus 0 multiplied by z1. Can you see? You get the very first equation. First row, first column. Cosine theta x1 plus minus sine theta y1 plus 0 multiplied by z1. You agree with me? So you get the first equation. Now tell me what would be in the second row, first column. So this is, for this matrix is a 3 by 3 matrix. First row, first column, first row, second column, first row, third column. Second row, first column, second row, second column, second row, third column. Third row, first column, third row, second column, third row, third column. So this is a 3 by 3 matrix. So tell me what would be here. Cosine theta 0. Then last column, last row 0, 0, 1. Remember this matrix. This matrix is called the rotation matrix about Z. It is called as the rotation matrix. And this rotation matrix is between 0 and 1. So if you write this rotation matrix is called as 0, 1. So we are relating the 0th frame and the first frame, and these two frames are related to each other by this transformation. Extremely important transformation. So cosine theta minus sine theta, cosine theta, diagonal 1, everywhere 0. In our robotics class, this is the only transformation that we are going to need when we solve forward or inverse kinematics problem. However, do you agree with me? Just like I have shown you the rotation about Z, you can have rotation about X. You agree with me? There could be rotation about X. What would be the difference in rotation about X? Do you agree with me? This matrix has rotation about Z. So can you see the last row, last column, since it's relating Z, has 1 in the diagonal and everywhere it's 0. If I ask you what would be the rotation about X, there will be 1 here, 0 here, 0 here, 0 here, 0 here, and these 4 terms, maybe with different signs, will be here. If I ask you what is the rotation about Y, then this, here, it will be 1, 0, 0, 0, 0, and you are going to have cosine sine terms over here. A word of caution. Whenever you are deriving the rotation matrix, be extremely careful about the positive and negative signs, because one of the signs, one of the projection is going to be negative. There is an alternate way of solving this problem, and this is not given in the books. So this formulation is given in the books. Now, if you want to formulate a rotation matrix, remember, what are we doing? Projection off, projection on. So projection off, projection off. And this guy is projection on. So we are taking projection off x1, y1, Z1. Projection on X0, Y0, Z0. Do you agree with me? Projection off, because our new frame is X1, Y1, Z1. Old frame is X0, Y0, Z0. Now I want you to tell me, answer me this. Look at the figure that I have drawn. Extremely important. Look at the figure that I have drawn. Tell me, what is the projection of X1 onto X0? Projection of X1 onto X0. Let X1 and X0. What is the projection of X1 onto X0? Which is nothing but cosine theta. You agree with me? Can you see that projection is cosine theta? So you have cosine theta. What is the projection of X1 onto Y0? What is the projection of X1 onto Y0? X1 onto Y0, sine theta. What is the projection of X1 onto Z0? 0. What is the projection of Y1 onto X0? Y1 onto X0. Y1 onto X0 minus sine theta. What is the projection of Y1 onto Y0? What is the projection of Y1 onto Z0? What is the projection of Z1 onto X0? What is the projection of Z1 onto Y0? What is the projection of Z1 onto Z0? 1. You get the same rotation matrix. Everyone understood this? So the way, and this, you will use this again and again. Projection off, projection on. So this is the new coordinate frame. X1, Y1, Z1 is a new coordinate frame. X0, Y0, Z0 is the old coordinate frame. We always project new coordinate frame onto the old coordinate frame. So projection of X1 onto X0 is cosine theta. Projection of Y1 onto X0 is minus sine theta. Projection of Z1 onto X0 is 0. Projection of X1 onto Y0 is sine theta. Projection of Y1 onto Y0 is cosine theta. Z1 onto Y0, 0. X1 on Z0, 0. Y1 on Z0, 0. Z1 on Z0, 0. Everyone understood this? And I will tell you the quiz problem that I'm going to ask you. I want you, and I have to do the same projections around Y and around X. Which means I have derived the rotation matrix when the rotation is about Z. You agree with me? I want you in the quiz derive rotation matrix when the rotation is about Y and rotation is about X. Everyone understood this? There are 3 ways you can derive this. And I will let you figure out the best way to find the rotations. I'm going to explain this once more because for my own satisfaction, because in our forward kinematics, inverse kinematics, once we find the rotation matrices, this rotation matrix will pop up everywhere. So first and foremost, we draw 2 coordinate systems. For example, since this coordinate system is the rotation about Z, I have drawn the original coordinate system and the rotated coordinate system. And then I drew perpendicular from the new coordinate system onto old coordinate system because I want projection on old coordinate system. And then I wrote this algebraic expression. X naught is x1 cosine theta minus y1 sine theta. Y naught is x1 sine theta plus y1 cosine theta. And z naught is equal to z1. So this relates the old coordinate frame with the new coordinate frame. Old coordinate frame with the new coordinate frame. And you can see those expressions are written in this direction. So you have x1 cosine theta minus y1 sine theta, x1 sine theta, y1 cosine theta, and last one is z naught is equal to 0. You agree with me? The other simple approach is start with this projection of the new coordinate system is x1, y1, z1. The old coordinate system is x0, y0, z0. So we are trying to find out projection of x1 onto x0, x1 onto y0, x1 onto z0. Same thing with y1, same thing with z1. Do you agree with me? Now, the quiz problem that I'm going to ask you to work on, and I'll set the stage. Why is this important? Because if you have a robot arm has typically the actual robot may have complicated geometry. But to solve the robot forward kinematics and inverse kinematics and come up with an expression, you need to come up or you need to draw a simplified diagram. That is called as the kinematic diagram. So to draw a kinematic diagram, we approximate robot joints two ways. Either the robot has a translational or prismatic joint, or the robot has rotational or revolute joint. So if you look at the previous problem that I have drawn here, this robot has a revolute joint and a prismatic joint. But this robot is shown in 2 dimensions. The actual robots are in 3 dimensions. So if you have a revolute joint, the revolute joint is shown as R, and that's like a hinge. So if you think about it, that revolute joint is like a hinge. And the prismatic joint is given as P, and that is like a cylinder. So if you think about it, it's like a piston cylinder assembly. So revolute joint, if you want to show it the simplified way, is denoted as a cylinder, and then you have the axis of revolution. Prismatic joint is shown as the brick. Prismatic joint is shown as the brick, and this shows the axis of extension. So you have a revolute joint and you have a prismatic joint. Now, in 3-dimensional structures or 3-dimensional machines, you can have revolute joints that are perpendicular to each other. You can have revolute joints that are parallel to each other. Now, I want to kind of think about the DoBot. Remember the DoBot that you used? So can someone tell me how many joints that robot has? So the example is, imagine the DoBot that you studied. Either you looked at DoBot or DoBot Magician. Tell me how many joints that DoBot had. 4. Ignore the last end effector. So 3. Are they prismatic or are they revolute? So you agree with me that the DoBot is a 3R robot, which means there are 3 revolute joints. Now my question to you is, how are these revolute joints arranged? So if you look at the kinematic diagram for the DoBot, so you have the first revolute joint, which is in the vertical direction. Then if you look at the second revolute joint, what it is actually perpendicular to the first revolute joint. So you have second revolute joint. And if you look at the third revolute joint, the third revolute joint is something like this. So what you have is, if you want to showcase or come up with a configuration, this is the first revolute joint, wherein the DoBot is rotating about the base. Then you have the second revolute joint, and then you have the third revolute joint, and at the end you have an end effector. So this revolute joint configuration, first revolute joint is perpendicular to the second revolute joint and is parallel to the third revolute joint. So this robot, the DoBot, magician or magician light, will be R perpendicular to R, parallel to R. Everyone understood this? R perpendicular to R, parallel to R. The other thing which I want to talk about is, when you want to solve the forward kinematics problem for the DoBot, all these geometry is given to you because these are the fixed link lengths are given to you. You would substitute the value of θ1. You will substitute the value of θ1. You will substitute the value of θ2. You will substitute the value of θ3. And you will find Px, which is the position of the end effector, Py, position of the end effector in Y, and Pz, position of end effector in Z. Now this position will be expressed in the inertial or the fixed coordinate frame. So you are going to have maybe a coordinate frame, and we'll talk about it at length in next class. But say you have a coordinate frame where this is Z, this is X, this is Y. And Px means the distance between the end effector and the origin of the frame in the X direction. Py means position of the end effector and the frame in Y direction. Pz is the end effector position around about Z axis. So for example, Px means how far this end effector is with respect to this X axis. Then Py means how far this end effector is in Y axis and how far this end effector is in Z axis. So Px, Py is Pz. So you will come up with the functions that depend upon θ1, θ2, θ3. Py is going to be function θ1, θ2, θ3, and Pz is equal to function of θ1, θ2, and θ3, because all the link lengths are given to you. All the link lengths are given to you. So you would come up with some type of an expression that relates these inputs. We substitute these values and get outputs. That would be the forward kinematics problem for the DoBot. Everyone understood this? Now, what we are going to do is, I'm going to show you some simulations. So I'm gonna switch my screen and then and here is the digital twin software. Okay. So what I want to do is go to Zoom. And then I'm gonna share my screen. Share. Okay. So